Ranok everybody, greetings with a happy new year from Ukraine. Let's our life will be peaceful. But today we will talk not about peace, we will talk about the real and engineering true and engineering stress and strains. If you doesn't know what is it, I really recommend to you to watch this video from Efficient Engineer. It's only 7 minutes and it explains a lot. It explains mostly everything what you need to know about true stress and true strain. But I want to show the way how to check this, how to understand this, and how to repeat this with your software. I use Ansys software because it's mostly simple to me. And we will show to you different species and we will test and show this result. So let's start. If you have a test machine for uniaxial compression or tension, you obtain from this machine some graphs which look, for example, like this. And this is the real strain stress curve which you want to use in your engineering calculation. But when you try to input those type of data in your computer software, it will not work. It will not give a chance to use this type of software. This type of data. And when you start to look at why, you will understand that the data which you obtain from the real tests are not real strain and real stress. It's engineering stress and strain. So you need to recalculate it, you need to input it, and only then maybe you have good solution. And today, during our task, I repeat the same process. So, I create static structural using Ansys Workbench, and for my task, I use and create 4 different materials. The first material, it's a standard material from Ansys Workbench. It's default material. It's linear, isotropic steel with this young modulus and with some data about tensile yield strength, about tensile ultimate stress, and for some of you this data maybe look like that this material provides not only linear behavior, but all these data, strain life parameters, ascent curve, tensile yield strength, compressive yield strength, and so on, are not used by software during the calculation. They used by software only for post-processing result. So you can change those digits and they doesn't change anything in your calculation, only on post-processing result and not only not on all type of data which you show. For example, if you demonstrate total deformation or strain or von Mises stress, it will not affect. If you show the data for factor of safety, which use those type of units, you will see different picture. Okay, so this is standard material. Structural steel, which called BLE, it's can be taken from engineering data source, general nonlinear material, and structural steel nonlinear. That's the one. I change his name to BLE because it's bilinear isotropic hardening material, which have those type of behavior. For 250 megapascals, it have the linear behavior, the same behavior as the structural steel, but after this point, material had changed his behavior and became a plastic and work with this level of stiffness, which in most cases for steels and aluminum are 100 times less than Young's modulus, around 100 times. So, and bilinear isotropic hardening have those type of curve for wall type of deformation. It doesn't stop anywhere, it continues to the infinitive values like isotropic elasticity, Young modulus in the linear behavior. Structural steel multilinear isotropic and structural steel multilinear kinematic was created from the structural steel linear by adding from those toolbox multilinear isotropic hardening properties to this one, and to this one multilinear kinematic hardening. They have the same type of curve, the same type of table for data for behavior. It's random behavior which close to some steels, but it's not real. It's only for understanding. When you create those type of data, please be careful with those units, because in a base they have a pascals, and if you, for example, change first material to megapascal, create those data and then copy to the another, it will not remember that you copy megapascals to pascals, and they need to increase data, increase values. So please be careful. As you can see, there are a lot of different type of plastic behavior. We will not talk about this for today. If you want to hear about this, please write a comment under the video. And these two materials present here for the simple reason to show that both of them will have almost the same behavior for current task. Okay. The next step is to create a test species, which we will try to load with tension. So it's a plane object, and it have 25 millimeters and 4 millimeters on a side. So we have 100 of square millimeters of section, and we divide it into a couple of type, a couple of parts of objects. This one and this one are used for create a fixation and to separate effects, boundary effects from fixation from the wall body, and this separate the thinnest part of our species if we want to analyze only this object. The length of the thin part is 100 millimeters, and those objects are almost random. You can draw it as you want. For our object, this length is 60 millimeters, and this is about 35 millimeters in radii, and its tangent here from this point. So these four objects are similar, and we need to add only one addition. We need to go from the design to the prepare tab in our Ansys discovery and use command share topology to share this topology between the bodies which contact each other to have a continuous mesh without any contact. Now, for better solution process. So when we create this type of objects, we can go to Ansys Mechanical. As you can see, we have 4 different parts from a lot of different bodies. We have 4 different materials here, and we have with this object material assignment, and we apply different materials to different objects. The first one is linear structural steel, the second is bilinear structural steel, and the next one is multilinear. And if we return to this engineering data, we can see that this object look only to the top, and these lines also look only to the top, only, not down, only up, only increase value. So additional very important things, it's for all 4 material we have turn on nonlinear effect. For the first object, because it's a linear material, it doesn't have sense, but for all others it's very important. And if for any of this object we turn from nonlinear effect from yes to no, this material will turn into the simple linear structural steel. Okay, as you can see, we have no contact. We have very important preferences on mesh. We change the type of mesh from quadratic to linear, and here you can find the video previously where I describe some difference in behavior with different type of mesh, and say that linear tetrahedral elements are not really recommended for most of types of analysis, but for our analysis, for nonlinear analysis with very big level of nonlinearities, it's the element, it's type of element which can be used because it's very stable, it produces stable solution. And accuracy can be achieved by increasing the number of elements and decreasing the size of elements. And we doesn't have here any bending in general, so we can use it. The size of our mesh in central part is 2 millimeters. You can use different size if you want. We use additional preferences to obtain the tetrahedral mesh here. We use the method and change from the automatic to tetrahedrons. It's not very important, but it can influence to our solution. With hex mesh, sometimes you will not have the full time of solution. It will stop in some moment. And also this method, it's compatible with adaptive, nonlinear adaptive region, but I try to use it, and for this type of case I don't use it, I suppress it, because it's hard for most of you will be to repeat adequate solution, because this is very good and very powerful tool, but it will have some difficulties in usage. So we create a type of preferences for our task which will not use this nonlinear adaptive region. So, and for the rest of the part, we also use additional body sizing. For this time, it's also 2 millimeters, but it can be meshed as it wants, so it meshed to the sweep with hex element. Okay, now let's talk about the different preferences on solution. We have fixed support, one fixed support for all these bottom faces, and we have a couple of displacement for every top face here. We do that because if we create the one displacement for all these objects, we will have possibility to obtain only one force reaction for all these objects at once. In reasons that we create a different displacement for different object, we can obtain reaction for every species. That's why we create the four displacement. But all these displacement have the same preferences. It have 50 millimeters of displacement for tension in those direction. It can be different in your model, depend on how you create your object, but you can understand in which direction you need to create displacement. And as you can see, it will change from 0 to 50 millimeters during the solution. The most important things is preferences of our analysis settings. And on step controls, we change auto time stepping into on and apply this type of preferences. Initial substep, it's 1000 step, and minimum and maximum substep, it's 10 times less for minimum and more for maximum than initial time steps. So firstly, it divide and try to move for the first step with 50 microns up, and then depending on how difficult or simple solution it will have, it will change the number of substeps to obtain accurate and most fast solution, something like that. We don't change all other preferences except a large deflection. A large deflection on, because we have here a large strain, and it's very important to have additional derivatives to obtain adequate solution. Okay, we solve this problem, and it have couple of bisections during the solution. For your task, this picture can have some difference, it's no matter. And we obtain this type of solution, and as you can see, they have the same level of displacement. This number is more than 50 because we have not only a change of height, it shrink, and this additional shrink also present in total deformation. If we take a look into directional deformation during the y-axis, we will see only 50 millimeters. Additionally, we have three different directional deformation at x. It shows to us the shrinks of the width of this object, and we can see that the first object with linear steel have decreased the size from 25 millimeters to 23. The second, with bilinear plastic behavior, double this value, so we have not 24 but 21 millimeters. And for the multilinear material, we also have the necking object, and in the thinner place we have almost 15 millimeters of width, but not 25. And the same situation we will have with the another direction. And the first species are not change his size very big values, only 150 microns. The second have about 0.2, and the last have almost 1 millimeters of change in thickness. This thickness was about 4 millimeters. So this is how they work. And now let's take a look into the elastic strain, and we can see that these objects have a lot of elastic strain and this doesn't have. We can take a look into plastic strain, and we can see that this object doesn't have plastic strain and this have, and we can see equivalent stress, and we see almost the same picture as equivalent elastic strain, and those three doesn't have any stresses. So let's talk about this result. First of all, if we take a look into our scale, we'll see that maximum stresses in those objects are 60,000 of megapascal. So it's much higher than any steel can provide. It's much higher than 250 megapascals, and so on. And we can watch to these blue objects and see that this object will be blue if they stress less than almost 7,000 of megapascals. If we change those objects to 250 megapascals, we will see that, sorry, not here, here, we will see that those object also has had some stresses, and this object almost full in plastic behavior, and this object have maximum of plastic behavior near the necking inside of this short inside of this thin object. So if we return to elastic strain, we'll understand that here we see the same picture. And if we take a look, we will see that 30% of elastic strain, it's not physical, it can be achieved in real life. And if we change here to 0.2%, which is almost equal to 250 megapascals, we will see the same type of picture as we can see in equivalent stress. Here plastic type, here plastic behavior, and this it's not plastic behavior, it's elastic stress, which is much higher. So why this object doesn't have any colors and look like translucent? Because this is linear object and it doesn't have plastic strain at all, only elastic. We can take a look here and we can see that we have 116% of strain. It's a lot of strain, mostly steels, even very plastic steels, erode and broke about 25-35%, so 3 times more we have. But the static structural, Ansys static structural type of analysis can't provide brokes here, so we doesn't obtain any brokes because we doesn't create description of how it must brokes and when. And now we can see that this object work very different. These two objects have the neck and this one doesn't have the neck. Why it's so? If we take a look into the plastic behavior of this object, we will see that plastic behavior arrive in the thin part of our species and then decrease not only the value but the volume of the presence of plastics behavior. And in the end of our tension, almost wall part became a plastic. Let's show it with this value. And now we have the next material, another type of material. It's fully plastic steel, which also have linear behavior, fully linear behavior. So it can't obtain any neck here because it works like this object but with the less level of elasticity. And the reason that here we have multilinear description, they can provide the neck as in real life, and we see this neck. And now let's return to this curve and see that this curve only look up, it doesn't look down. And now we can take a look to our reaction forces. The first reaction look like almost linear, but we will return to this later. The second have this part and this part of behavior. And this part of behavior doesn't look linear. Here it looked like it became more and more horizontal. And if we take a look to this one or to this one, we will see the same elephant as we can see in real life with real species. So it has the linear part, then we have these parts of behavior, and then it tried to look down. So why those reaction look down? We need firstly return to this video which describe and to these two formula which is present even on preview to recalculate engineering strain and stress to the true stress and strain. And this is it's engineering. It's engineering forces which it's force reaction, and engineering stresses calculates in very simple way. We take this value and divide it by the area of section of this object. So we divide it by 100 square millimeters. But this graph doesn't, this recalculation to the stresses doesn't include the fact that during our elongation, during our tensile, the area of our section are changed. That's why if we copy those results from the force reaction into Excel and create a graph, this orange one, it's how we obtain our reaction. And during the linear calculation, during linear static analysis, we obtain non-linear reaction. It's how it's possible. And the reason is very simple, because in the end of our calculation, the area of our object are not 25 and 4 millimeters, but 23 and 3.7. So the area changed from 100 square millimeters to 85 square millimeters. And this is how it will look if we take into account the change of our area. So it's when we recalculate. The same situation for plastic behavior. This is how it should look, including the change of our area, section area, and this how our graph of stresses look like if we don't take into account change of area. Additionally, I need to say that the x-axis here is not the strain, it's the time. We take from this one. So to obtain strain stress result, you also need recalculate strain graph and put it here. So, but the most important, it's this elephant. And we have couple of segments on this curve. The first segment is when we work linearly. The second is when plastic behavior started and our section sorry, our section decreased, but it decreased for wall this part, and after we start obtaining the neck, which dramatically decrease the section, we obtain this type of behavior, because in the end of our tension, the thinnest part have only 30% of area compared to the previous 30 square millimeters. So these numbers should be multiplied 3 times, 1, 2, 3, to obtain the real stresses and the real graph. But in reason that we check the force reaction as we do it in real life with real species, and don't take into account the change of the section, we obtain that our graph and reaction and recalculated with the constant area stresses will look down. So you can create graph of movement in different direction for some point of your construction, and this will help you to obtain the real value of the section of area in this moment of time. So you can recalculate this curve and obtain more realistic curve with the real stresses, but not imaginary, not the engineering stresses. And the same situation with elongation with strain. And when you work with those type of result, when you have big neck, you need to understand that in difference from this object, which is elongate with almost full geometry and almost full this part of geometry, thinner part. After we obtain neck here, the most deformation we have only here in the necking, and these parts are almost not deformed. So we should be very careful when we recalculate and when we try to evaluate and when we try to understand the graph and value of stresses, of strains in our real tests, in our physical tests, not only computer, in real. And yes, it's real because it's made in a real life, but in reason that we don't include into our calculation some very important facts, it's engineering stresses, it's engineering strain, but not real. And if you want real, true stress, true strain, you need to include as minimum those type of formula with logarithms, and mostly the whole information about the behavior of different part of the species. So as you can see, with those type of data, we obtain the same type of behavior as in real life. And now I explain why those data which you obtain from the real experiment in real life need to be recalculated, re-explained to use properly in the computer-aided engineering software. And it's no matter will you use Ansys, SolidWorks Simulation, FEAMAP, Nastran, Altair, Hypermesh, and so on. It's no matter, it doesn't depend from the software. It depends from the physics and engineering approaches. So, try to repeat it and ask a question if you have, and have a good year.